Hello, I wanted to go ahead and fill in the rest of that review that we didn't get to in class. I'm making this for a couple of classes, so I'm not sure exactly how far we got, but I'm going to start from number 10 and move on. I think on number 9 in both classes, we had got to talk about symmetries, and then we ran out of time. So we didn't get to talk about the transformations or how to combine functions. So I'm going to do that now and put that up so you can have something to kind of go by while you're studying, in addition to just the review sessions that we've been doing. Okay, so here's what we're going to do for our screen share. I move that out of the way. All right. Okay, so I want to start with number 10 down here where we're talking about transformations of functions. Okay, so I have a couple of examples. Number 10 is a specific type of key graph that we're moving around. And then number 11 is a different key graph that we're moving around. And then number 12 is yet a third key graph that has already been moved. I want to see if we can write down the expression that has the transformations that would produce this graph. So these are all things I want you to be able to do without graphing. This was a handout we had done in class over section 4.1 the first day. So I'm just summarizing the stuff on the shifting right here. But this is the basic idea. If you want to take the traditional graph of something and slide it from its traditional position left or right, that is done by adding or subtracting a number to the x. The f out here is just any of our key graphs, f of x. So this really would be replaced with the absolute value around this. If it was an absolute value, or if we were squaring it, there'd be an exponent on the outside of the 2, or a 3 for cubic. If it was the square root function, all that would be under the square root sign. So there is a number that's being added or subtracted directly to the x value before we do any other calculations. That's how you know it's a horizontal shift. The x value is being adjusted. All right, and we talked about this before. It's the one that just goes the opposite way that you might guess. X minus a number will shift to the right by that many units. X plus a number will go left by that many units. So if they're adding or subtracting a number to the x, it is a horizontal shift. Subtraction moves right, adding moves left. All right, if instead we are talking about making a graph shift straight up or straight down, but not move sideways, that's controlled by a separate term that gets added on after we do all the other calculations. So it's its own constant term. And this one is more straightforward. If you add a number, it goes up. If you subtract a number at the end, it shifts down. Okay, and then, so that's how you do left, right, up, or down, is by adding or subtracting a number either to the x initially or as the very last step for vertical shift. If I need to adjust the orientation of the graph from, say, the standard position, I just picked 3 of them like this, to the flipped upside down position. You know, we studied parabolas and said if it's a negative in front of the x squared, that's going to make it go downward from the vertex. So anytime there's a negative multiplier. Same thing for all the other functions. So whatever, if the normal function is moving upwards, but from the pointing part on absolute value, negative in front of that, we'll flip it upside down. There's positive square root, negative square root. All right, so the multiplier that sits out in front of the calculation where the x is, that tells you whether it's right side up or upside down, positive versus negative. But it also can tell you a little bit more about the actual shape of the graph, whether it's just standard width of a square or square root or cube or whatever, or whether it's a little skinnier than normal or a little stretched out and flatter than normal. Okay, and so that has to do with the actual size of the number itself. So that's the last thing down here. If the size of the number, regardless of which way it's facing, the positive or negative, if you have a number that's a multiplier that's bigger than 1 or less than -1, so like does this include numbers like 2, 3, 4, or -2, -3, -4, that's going to make the graph look more narrow. We call it a vertical stretch, but it would be more skinny looking compared with the standard width. So these are more, the arms are closer together. It's rising faster than it's going across. But if you have a multiplier that's a little decimal or a fraction, whether it's positive or negative, and that decimal fraction is less than 1, okay, then you're talking about a vertical compression. So it's going to look flatter or wider. So here's a couple of examples of something that would have had a multiplier that's less than 1. It flattens it out a little bit more. Okay, so those were the kinds of things I want you to be holding in your mind when we look at this problem right here. So in number 10, we have an absolute value graph. We have to look through that and look at everything that isn't a number being added or subtracted or multiplied. This is like 1 is like my H, 2 is like the K, 4 is like the A value, that's the multiplier. The only other thing that's happening in here that isn't one of those add, subtract, and multiply is taking the absolute value. So that's how we know what the basic shape is going to look like from the absolute value. So the key graph is absolute value. And I do something similar on the test. So you can just look up where all the lists of our key graphs are and pick one of those. You can do this to any graph, but we're going to go with starting with the simple key graph shape. Right, so the key graph is just plain old absolute value. Now the horizontal shift has to do with the number that's being added to the X. So since it's +1, we said on our sheet earlier, if you add 1 or add a number to X, it shifts to the left by that many units. So it's 1 unit to the left. The vertical shift is the other add or subtract number. That's the one that's on its own, a separate term. That means we do whatever the regular Y value is by computing it, and then we drop it down 2 units. So -2 is a shift down by 2 units. Okay, so for some reason, I needed to focus in a little bit better on this one. Maybe like that. So if this was regular absolute value right here, that's the key graph right there. This one would be every point on this one has been moved 1 unit to the left and 2 units down. So the whole thing left and down, I'm just going to focus on this point and then kind of the middle point. If I shift it, I can kind of draw the rest of it in automatically. So we're going 1 unit to the left. So this would shift 1 unit to the left and 2 units down. So 1 unit to the left, 2 units down. We'll put the new vertex here. And then I would just draw the absolute value graph. And I'm not asking you to draw it on the test, but I do want you to have a mental picture of what this should look like without having to run to Desmos or something and graph it. All right, so that's why we talked about transformation. Let's talk about the rest of it. The key graph is vertically either stretched or compressed by a factor of whatever that's referring to this number right here. So factor of 4. Since 4 is bigger than 1, that means it's going to be a steeper type of look to it. So that's what we call a vertical stretch. If it had been 0.4, 0.04, 4/21, some fraction or decimal less than 1, then that's a compression. Okay, now if we go to number 11, now we're just drawing a sketch by hand. I probably, if I did something, well, I might do this on the test. I'm not even going to lie. So let's see, key function. Let's look through here. There's a minus in front of it. That would be like our A value is -1. So that would tell us it's got a traditional shape, but it's going to be flipped upside down. This tells me that the H value is 2. So that's going to be a horizontal shift. And then this is the K value that's added later here. So the key function is the one that's not any of those. That's that little cubic there tells us that the key function is the cube or the cubic function, the X cube function. All right, so the transformations. The -1 means it's going to be flipped upside down. We could also say reflected across the x-axis. That's the math term, across x-axis, but really it just means starting from where the normal, the x-intercepts would be, or that the middle of the graph, we flip it around. All right, and then the -2 means we're going to shift horizontally, but to the right by 2 units. And then the +1 means we're going to go up 1 unit. Okay, so if I were going to graph it, I'm going to go ahead and kind of sketch in the cubic, the key graph that I'm moving around. I'm not really going to, this isn't really my graph, but it's the X cube graph that I'm going to kind of be visualizing in my mind, like it passes through the origin right there. Not very pretty, but it's supposed to keep more curvy like that. But anyway, there's X cubed basically. But I want to take this graph and do these changes to it. So it would be flipped upside down, but I'm not going to draw it in yet because that would be 3 steps. If I'm flipping it upside down, would have it descending, going through the origin, and then going in the second and fourth quadrant. I'm going to wait and draw that in later, but I'm going to move this point around, then I'm going to draw that shape through it. All right, so I'm going to do the right 2 and up 1. Every single point here is going to shift right 2 and up 1, and then flip upside down, but I'm just going to move the first one. So there's right 2 and up 1. So this point shifts over here. So this is the new point that I'm going to draw the new shape through. So there's my vertical and horizontal shifting right here. And then I'm going to flip it over when I draw in a cubic graph. So it's going to fall kind of flatten out as it goes through that point and then continue to fall. And again, not a very good drawing by hand. That's why we go ahead and do these things together. All right, so do them just kind of visually. So pretty sloppy, but it's the basic idea. Flip this upside down, shift everything right to up one. That's what it would look like. Hopefully, if I gave it something to you on the test, it would be a nice grid. Be easier to work with. I'm just doing it freehand. Okay, so let's look at our last one on these transformations, which is, what is this? We're showing it to you, and it's on this one, I went ahead and said it's x squared, but I'm hoping because we did 2 sections on parabolas that everybody would notice that it's a parabola, so that's some variation on x squared. So the key graph is x squared, which normally has the turning point here at 0, 0. X squared normally comes through like that. So we're trying to think, how did this move over here, right? So let's figure the horizontal shift. It goes from the starting place, which is our standard position. It moved 1, 2, 3 to the left. So when we talk about the movement, we're saying starting from the traditional position of the graph, how did it move to get to this new transformation? So starting from the origin, that's where normally the vertex is. The vertex is the easiest one to identify on the shifting. It moved left 1, 2, 3. So it went left 3, starting from here. Now, how far down did it go to get to from this point to this point? So here, this one's sitting on the x-axis. This one is dropped down 1 unit below. So it's gone down 1 unit. All right. So if we try to put that together, my x is being squared, but there was a horizontal shift. So I'm going to do x plus or minus a number. So left 3 is the one where we add 3. And then down 1 means we subtract 1. Okay, so where is my zoom? Yeah, I'm letting the dog in, so hang on just a second. Okay, so the last kind of problem we're going to do, let me get this share back up here. Okay, so the last thing we're going to do is the combining of functions. And so just remember that in the same way that I'm going to use for the plus, it just means if I use the regular standard function notation for each function separately using this same input and then just put that same operation in between. This says add, so we're going to add. Then you can think of it as just replacing. So f of x, I'm going to replace it with what the f of x expression is. That's 5x minus 2. This plus sign is that plus sign. And then after the plus sign, I'm going to write out the expression for g of x, 2x plus 4. So just follow that as the guideline and then take a fresh look at it and see how you would simplify it. So in this one, we have some like terms. So I'm just going to take the 5x and the 2x and call that 7x. Negative 2 plus 4 would be 2. So scoot that back a little so we can see what I'm doing here. All right, so that would be our answer for the first one, simplified. But you set it up first around the plus sign. If this is subtraction and you have 2 terms in the expression that follows, make sure that you subtract each term using parentheses. So that's what you do when you have the combination of 2 functions and there's an x. That means your answer is going to be an expression that also has x. It's just another type of function. All right. If instead, though, we have the combination and they have a 1 or some number here, like a specific value to plug in for the x, you can either go ahead and do it in the general case with the x and get it simplified. And then once you get it simplified, plug that number in for the x here at the end. Or you can just do it separately and then subtract the answers. They'll give you the same answer. So I'm going to write it at the start the way I've told you to write everything, which is to write each function separately with that input and then put whatever the operator is in between it. That's true for plus, minus, times, and divide. Now I'm just going to actually do g of 1 separately. So g of 1 would be 5 times 1 minus 2. Would be 5 minus 2 would be 3. That says minus. Let me put parentheses here just to make sure. F of 1. Oh, wait, I messed it up, didn't I? Oh, wait, no, that's f of 1 right there. So 5 times 1 minus 2 is f of 1. I went the wrong way. F of 1 is there. G of 1 would be 2 times 1 plus 4. So here I should have written 2 times 1 plus 4, my mistake. I want to make sure and get the order right. G of 1 means I got start with this one. 2 times 1 plus 4. And then f of 1 means I do the 5 times 1 minus 2, get those two answers. So this one is 3, 2 times 1 is 2 plus 4 is 6. Then I subtract the answers. So the final answer is going to be 3. So 3. So if you have a number, you have the combination of functions and there's a number showing as input, you should have a single number showing for the output. If x goes in, something with x comes out. If a number goes in, a number comes out. All right, so let's look at this next one. This one, a number goes in, so a number should come out over here. But this just means plug in 0 to the top function, plug in 0 to the bottom function, and make a fraction out of that. So f of 0, go back up here, 5 times 0 minus 2. G of 0 be 2 times 0 plus 4. It gives us negative 2 over 4. That reduces to negative 1/2. Number goes in, number comes out. Okay, we have a couple more of these, and then we do composition, which is a different one. So this just means f times g, and notice it's the general form with x. So this means we're going to take the first expression and multiply it times the second expression. Well, our first expression, 5x minus 2. Second expression, 2x plus 4. And then we're going to be asked to simplify this. It does say simplify all answers. So we're going to FOIL this out. So 5x times 2x would be 10x squared. And then your inner and your outer, you get negative 4x and positive 20x. And your last times last would be negative 2 times 4 is negative 8. Those two go together. So my simplified answer would be 16x minus 8. Okay. X is the input, an expression with x is the output. Same thing on part E. I have a general expression. This just says subtract the two functions starting with f of x. So earlier we had done subtraction with a specific number. Of course, we're also starting with g. So here's another subtraction. This time we're going to start with f and we're going to keep it in the general form. So again, this means take the f of x function and subtract the g of x function. So f of x is 5x minus 2. Make sure I get my order correct this time. Minus. Now g of x is 2x plus 4. I want to make sure all of that is subtracted. So I need to put parentheses around anything that's being subtracted that has more than one term in it. That really means I'm going to subtract each of those. So it'll be a minus 2x and a minus 4. If you don't do this, you may drop the sign and get the sign wrong on this last term, and then your answer is going to be wrong. All right, now let's look and see if we can put together our like terms. I have 5x minus 2x will give me 3x. And then I have negative 2 minus 4. Should be a minus back here. You had to flip signs because it was being subtracted. So that's minus 6. Okay. All right, and then the last one on this plus minus times divide is multiplying two values together because there's a number that's being plugged in. So I'm going to plug one into the first one, plug one into the second one. Notice I already did this earlier. I worked out f of 1 earlier. That is going to be f of 1 is going to be 3 right here. F of 1 is going to be 3. So f of 1 is 3. G of 1, I worked that one out earlier too. G of 1 is 6. So this time we're multiplying those two values. Okay, so see how both times when we plugged in 1, we're working with the numbers 3 and 6, but up here it said to subtract them. And then down here, it says to times them. So we're going to get 18. Okay, and then the very last thing is this composition of functions. This is different than all the other ones before. Composition means the one that's right next to x, that entire function, either the entire expression or the result from plugging something into that entire expression, all of that is going to replace the x, or it's going to be used as input to the outer function. So the outer function is the general structure of the thing, but what we're going to replace the x with is the expression for the inner function. So what you might think of is the outer function tells you the general structure. So the outer function on this one is f, and it says 5 times the input minus 2. So the way this is written, since g of x is the one that is next to the x, it's the interior function. It gets plugged into this one. So what I'm doing is I'm taking this entire expression and I'm going to drop it right there where that x is. So all of this is going to replace the x in the first one. So think of it like this. The first one is telling you the basic structure. So since f of x is 5x minus 2, this is going to start off with 5 times something minus 2. Now the something is the other function. G of x, I'm just copying it so I don't have to keep moving the paper up and down. This is the other function. That's going to go right here. 5 times 2x plus 4. See, that's what I'm doing. I'm replacing this with the actual thing it is, equal to 2x plus 4. But the overall structure I'm building around it is from this one. So maybe think about when you're doing the general form like this, write out the general form for the outer function, but every place there's an x, just drop a set of parentheses and move it on. So 5 times parentheses, leave it blank, minus 2. And then what you put between the parentheses, go look at the other function. That's what goes inside or replaces the x in the f of x function. Okay, so the theoretical one's a little harder to explain. There's different ways to explain it. So I'm going to go ahead and simplify this. This is constructed correctly. So now I'm going to distribute that 5 and I'll get 10x plus 20 minus 2. So it'll be 10x plus 18. Okay, so that's how you combine the steps from both functions together and simplify it a little bit. Okay, now I have a hint on part H, but it doesn't have to be done the way that I said it, because it might be the case that I just ask you to compose with a number and I don't have you do the general case first like this, but it's the same idea. We have g of 1 is what's going to be used as input to the f of x function. Okay, so if the f of x function is still 5 times something minus 2, right? I need to figure out what g of 1 is. Well, g of 1 is going to be 2 times 1 plus, we've done this before, will be 2 times 1 plus 4 will be 6. So g of 1 is 6. Okay, and then work that out. That's 30 minus 2 is 28. Now, that's not the way that this just says plug 1. Notice that since I already did it in the general case up here, since I do have an expression like that, it has the steps already simplified. I could just streamline it for this particular example and plug 1 in there and I get 10 plus 18, also 28. Okay, but just in case you're given just the 2 general functions and then plugging a number in, you can always do it this way. So let me do one more example of that, just to make sure we understand it doesn't have to be the same thing. You don't have to have the general case to do the specific number. So let's say if I'd ask for f composed with g of, I'll say 10. Okay, this means I got to figure out what g of 10 is first. So 10 goes into g of x. We figure that out. That's what this is. Then I'm going to take that. I'm going to replace it for the x over here. 3 times whatever minus 7. Okay, that's what this means. It means we're going to take g of 10 and we're going to use it as input to the f of x function. That's what composition means. So I'm going to take 10. I'm going to run it through the first one over here, 10 squared. So g of 10, I'm just making a note to myself over here, is 100 because I'm squaring it. So what I'm going to use is 100. I got 100 out of this. I'm going to plug that into f of x. So I'm going to do f of x. We'll do f of 100. So 3 times 10 minus 7. 300 minus 7, 293. Okay. So if you have 2 functions given to you and you have a composition between the 2, if it's a number here, you don't have to do the general case with the x's like we did on the practice there. You can start with that specific number, plug it into the function nearest it, 100, and then take that answer that you got out of g of x and use as an input to the next one. So now we're going to put 100 in here, because that's the next function out. 3 times 100 minus 7 is 293. Okay, so that's at least the rest of the review that we didn't get to in class. I'm going to go ahead and stop this so I can upload it, and you guys have something that you can read through or play if you need more help with that. Okay, and don't be late to class on Monday. Make sure you're there plenty of time so you feel relaxed when you're testing as much as possible. All right.